So yes, what kind of predictors are we talking about is the question. Time invariant, right? Give me some more synonyms for those. Yeah, person things. Stuff you've measured once. Time invariant is kind of a mouthful. I sometimes hear time constant. If you like that one better, I'd accept that as an alternative. The alternative for level 1 is time varying usually, so then people say time invariant, but time constant is perfectly fine with that. And their job is to do what? What are they for? Predicting people differences, which, give me a more technical term for people differences. Level 2, yeah, random effect variances. Yes, that is what they are for. So the idea in models of change is that they would moderate the growth curve. So they can make your intercepts higher or lower, make your slopes steeper or shallower, that kind of thing. And in so doing, they would predict the U variance that goes with their corresponding equation is, so long as there is one. ... We'll put a pin in that for next time. So do you want to go back through, in this example, we have an unconditional model. Would that be a reasonable place to start? Okay, so the story of this again, 6 sessions of practice in this task. The outcome is response time. I'm starting with a 2-piece slope model because this one will be a little bit easier just to start with, and because this would be a common thing people would want to know. How does change, how do person level predictors moderate change during each period of a study? It's like during a baseline period, during an intervention period, and so forth. So this model then, if this were our best unconditional model of change, this is a new baseline. So from the perspective of level 2 here, each of these level 2 equations defines a different person-specific outcome. We have an intercept, we have the first slope, we have the second slope. So that means that from this perspective, these are essentially empty models within each here because there's no predictors yet. So conceptually, like U0 here represents the idea of all the reasons why people need their own intercept. We're going to put in some reasons as person level predictors and see how the U0 variance decreases. Same idea here. Beta 1 and beta 2 are all the reasons why people need different slopes. So we can put predictors in here and hopefully see the U1 random linear slope for 1, 2 decrease, and then U2, the random linear slope for slope 2, 6 decrease as well. And in terms of trying to compute model predicted effects of your predictors, you don't need any of the random effects, you just need the fixed effects. So from this model, like if I wanted to predict what is the expected response time at any occasion, these are the ingredients that I would need. And what would go into slope 1, 2 and slope 2, 6 are the values that you used in making them in the first place. So for instance, slope 1, 2, if I go back up to the R code here, is coded 0 for the first occasion and then 1 after that. So if I'm building a predicted outcome, I know that slope 1, 2 would either be 0 or 1 based on which occasion I'm predicting it with. Likewise, slope 2, 6 varies between 0 and 4, and I would put in whichever corresponding value I want the occasion for if I want to predict an outcome. Okay. That is, let's see, that's the equation. We went through the Stata code last time, I think. We went through the R code as well, if I remember correctly. Stata folks, do you understand what this stuff is about, or do you want to go over that again? We do not understand, Vladimir says. He's shaking his head, but I'm not sure at what. It would be good to review. Okay. Yes. So I've answered a few questions in office hours from both classes, actually, about what this is doing, so I figure it would be good to go back over it. So the idea here is that what I want to know before putting in any other predictors is how much variance did the fixed effects of time explain? So that'll be like step 1, and then I start adding predictors and see how much new variance I've explained with those. To do that, conceptually what I want to do is take this number right here relative to an empty model and see how much less this number is relative to that. So I can do that by creating predicted outcomes So first step here is to create a predicted new column in the data set. That is, I'm calling this pred p-unc for piecewise unconditional model. And then I'm correlating that with the real one. That correlation squared is my R square. So that answers the question of the overall variance in response time. How much is because there is change on average? 4% of it or so. Okay. Now in preparation for subsequent models, because this is my new baseline, like these are the random effect variances that are going to be subsequently explained by my level 2 predictors. So I need to save these values so that I can watch them go down and then I can compute the change in these values. So how I am doing that, step 1 is to save the output from this model into an object, and the object is stored as a matrix. So I'm saving a matrix under this name, and in Stata, by the way, you have to run things sequentially. So like if I run this model and I go back and do something else and run something else, and then I go back and run this again, it doesn't know which model it's tied to. So you have to run them like immediately in order for this to work. So step 1 is to save the results. Step 2 is to print the results. Okay, my screen just went blank. To figure out where they are. So matrix list then prints that saved object. And it is a matrix that is so big I had to put it in as an object so it would fit. It has 9 rows and 10 columns. The first row is what I want here, that is the estimate. Now the first 3 columns here correspond to the first 3 parameters in the output, which are your fixed effects. And these ones are labeled relatively straightforwardly. Like I could look at the label here and guess what these things are. After that, I have no idea. LNS1 underscore 1 underscore 1 colon const. Someone, anyone, tell me why that makes sense as a label. And note the consts on all of these things too, which is just mean, because these are not all related to an intercept. But here is how you figure it out. They go in order. So if you think of these as going down rows of your output, transpose that into going across columns instead. And then we know that the 4th thing here, this 4th column refers to the first slope variance. The next column refers to the second slope variance. And the 3rd column refers to the intercept variance, because that is the order in which they are listed here. After that comes the covariances, which I don't need to save, and those are the ones that I've discovered through trial and error have an ATR in front of them, for reasons, I guess. And residual variance is always last. So what I'm doing in the next piece here is saying go to row 1, column 6, so 1, 2, 3, 4, 5, 6. That is my intercept variance. Column 4 is slope 1, 2 variance. Column 5 is slope 2, 6 variance. And then column 10 is the residual variance. So if you use this type of code in one of my examples and you try to repurpose it for your problem, you will need to verify that these numbers are correct. And you can either do that by counting your output or printing this table or both. Now the second part of it is figuring out what the hell these numbers are, because they are not what they look like. So for instance, the residual variance according to this table is 4.88. If I go out to up to the output, it is not 4.88, it's 17,673. That is because what is being stored here is the log of the standard deviation that goes with that variance. So I have to untranslate that back into variance metric so that I can look at the change in the variance. So I am unlogging it by exponentiating and squaring to get it back into variance from standard deviation. And to be clear, I did not come up with this. I asked the Google, what the hell do these numbers mean? And someone had figured it out and told me. So I stole someone else's code. So I am saving each of those numbers with a name so that then I can type in the name later and it will fill in that number and do the math for me. So the reason to go to the trouble to do it this way is that theoretically this code should work for any kind of similar model so that you don't have to retype in specific numbers, and that would be much more prone to error than letting this do it. I'm sure there is a way to make a function out of this that does this more automatically, but I do not have the skill set yet to do that in Stata. I can do it in SAS, and I'm now learning how to do it in R, but Stata is the final frontier. Okay, so then down here, I am using some of those values, such as the intercept variance and the residual variance, to compute reliability coefficients using the formulas given in lecture 5. All right, does that help? Big nods, okay. And our folks, the process is basically the same for you. You have to figure out where it is and what it's called and how to get to it. And that's usually like most of my trouble, is that part. So I used a manual function here. I'm asking for predicting the outcomes from the fixed slopes, correlating them with the real ones, printing that correlation, finding it inside the object and squaring it. And then I wrote a little function that does those steps for you. In terms of finding the variances in R, they are stored in an object or a function that pulls it. I'm not entirely sure what the right language is here, but it's called varchar. And I work best when things are in data frames. I don't know how to handle tables or lists or things of other kinds of objects, so I converted it into that. So then I have a matrix looking thing here. And so then I'm doing the same thing in Stata, saying, okay, take this name and assign it that spot right here, row 1, column 4. For slope 1, 2, it would be row 2, column 4, and so on. And so now these are objects that I can then have it do math on when I feed it into the instructions, like right here. Okay, questions on any of that?
So
No.
you mentioned how to interpret the reliability of intercepts for an instant. Is that like the consistency of this value across multiple times?
It would be like if you think of the intercept as like a latent variable that's being measured by these 6 observed indicators. This would be an index of reliability, like how much of the variance is due to people differences as opposed to residual differences. So most of the variability in this data set is between persons. Like at the interclass correlation in the unconditional empty model was 0.82. So I do not see this a lot in longitudinal studies. I see this more in cluster data. They want to talk about the reliability of a group mean and whether there's enough of a signal there to do things at the group level. But for the sake of completeness, I thought I'd throw it in here too. And the slope reliabilities, I would not really think of them straight as reliability. I would think of them as the amount of signal due to individual differences relative to the amount of noise around the signal due to residual. That's how I would think about it. So your slope reliability is a function of how different your people are in their slopes. If they're not that different, you're not going to have that much reliability. But it's relative to the residual variance, relative to the error around the lines. So of like the variability that's related to time, how much of it is like a signal due to individual differences versus residuals around those individual differences? That's how I would think about that. Okay. So let's look at a predictor. We did this last time, but we'll wade our way back in. So in the world of cognitive aging, no one will believe a word you say unless you've controlled for biological age, chronological age first, because that's the more uninteresting reason why people would differ from each other. So we're going to do that. So I have what I'm calling time is slope 1, 2 and slope 2, 6. That's change over the 2-week period across the 6 sessions of measurement. Age is time invariant here. So age gets an I because it does not vary across t times. I am centering it near the mean of this variable in the sample, and I am putting it in 3 different spots because there are 3 different ways people differ from each other. Then to determine, oh, go ahead, please.
So we're counting age as a time invariant predictor
That's
because
correct.
we only measured it once, even though technically they are aging throughout the study, and some of them maybe had a birthday during the study, but we're just taking their measurement at their age at the first time, first session?
Yes, so I have essentially time is in 2 spots in this model. I have how old they were when they walked in the door,
Okay.
and then the slope 1, 2 and slope 2, 6 is how much time has passed relative to that point, but it's not measured in days or weeks, it's measured in opportunities for practice.
Okay.
Because I would argue that if you're 80 and then you're 80 and 2 weeks older, like that's not a significant difference. That's like the 2 weeks is not aging per se, it's the opportunity of the practice. But technically speaking, you're right, they're confounded. Yeah. I'm sort of splitting it into the effect of being older and then the effect of getting older or getting more practice in this context. Yep. So in terms of these interactions, lots of practice with this. You'll get a chance to do more practice in your last homework as well. I can talk about how the first slope varies as a function of age, and this would be the ingredients I would need to do that. So to begin with, I would need slope 1, 2, and then I would need to incorporate the interaction term of slope 1, 2, and 80, which is what this is right here. Same thing with slope 2, 6. I need that as a starting point, and then I can incorporate the interaction of age by slope 2, 6 and fill in whatever values of age that I want. So the main effects, as I will call them, of slope 1, 2 and slope 2, 6 are specific to an 80-year-old, but the model tells me what those slopes would be for any age. Likewise, spinning it the opposite perspective, the main effect of age is specific to session 1 because that's where slope 1, 2 and slope 2, 6 are 0. But the model still tells me what the expected age effect would be at any occasion by filling in the values for the predictors at that particular occasion. And the overall fixed effect that is being built by the model in terms of y hat here is given right by this. And so this is what would go into the total r square, is all of this stuff. So then to get all of those pieces, we have the two main effects of time, the main effect of age, and then the interactions of the slopes by h. Saving the results. This test right here, you have seen this maybe a couple times, but not a whole lot. This is a generic way that you can do multivariate Wald tests in Stata. So by default, they will be true multivariate Wald tests using chi-squares. The small option here changes them into Fs using whatever denominator degrees of freedom method you had mentioned in your code. So this is using Satterthwaite, for instance. So I am asking, with this command right here, did those three age slopes as a set improve the model prediction? You can think of this as analogous to F-tests for the change in R square in single-level regression models. So like if you have a block of predictors and you add another block of predictors, you can compute the F for the change in R square. That's what this is. It's the same idea. In terms of getting expected slopes at different ages, here's an example of how one might go about this. So I have plus or minus 1 standard deviation of age as the moderator. The margins command with the option dy dx in Stata is giving you the slope that's in parentheses and then at various values of the moderator, where this is start at minus 6, go in increments of 6, up to 6. So this would give me, given that age is centered at 80, the predicted slope 1, 2 at 74, 80, and 86. And then the same thing down here is happening with slope 2, 6. So these lincoms are doing the exact same thing as this one statement. I just wanted to make it more explicit what's happening. Same thing here with the slope 2, 6. And note I'm holding slope 2, 6 at 0 for this one, and I'm holding it at 1 for this one. And then the age slope. The other way to think about it is, how does the effect of age vary across practice? Does age matter more before people are practiced, or does it matter less? So to do that, I can get the slope of age conditional on time, and since time has this piecewise structure, I did it in 2 sets, where I'm going from 0 to 1 for slope 1, 2, holding slope 2, 6 at 0, versus holding slope 1, 2 at 1, and then going from 1 to 4 of slope 2, 6 for these ones. And the small, by the way, you do have to write this after every single thing, otherwise it defaults to z-tests instead of t-tests with degrees of freedom. I'm sorry?
Can you repeat that?
Yep. So the small here, what that is doing is changing the hypothesis test that you're given from a z value with no denominator degrees of freedom to a t value that uses whatever method of degrees of freedom you specified for your model. So by default, you get z's and chi-squares. You can change it into t's and f's with these, with the smalls for tests and lincoms and stata. And then I'm getting some means, and then I'm getting change in R-square. So doing the same thing, predicting response time from my new column that is saved as predictions from the fixed effects, saving that as an object, printing that object, and then computing the change in R-square so we can look at that. And all of the numbers will be given in the R output instead. Then this part is saving all the new variance components so I can compare against them. Note the numbers have changed. All of these values have changed because the table has changed. So they should all be 3 more than what they were before because we've added 3 fixed effects in the front end. And this is the shorter version of the pseudo R-square formula with less typing, but it's the same concept. How much by how much did each go down? Okay, questions on the stata aspect, and then we'll switch to R. Okay. And then R folks. So we have the same principle here, adding in a main effective age and the interaction terms. Note that a colon is just the two-way interaction term. If you use an asterisk instead, it gives you all lower order main effects and the interaction, so less typing, but less transparent. Okay. Can we do the interpretations one time? I think we did this last time. Why not? We're all here. Intercept, what's that tell me? Average response time of an 80-year-old, and I would say it's session 1, which is time 0. Yeah. So instead of just having a reference point for the intercept, in this model we actually have a reference point for the growth curve. So I can say that this is the change from 1 to 2 for an 80-year-old, and this is the change from 2 to 6 for an 80-year-old as well. Same idea. So these are rates of change in this case. This is only one difference, so there's not much difference, but this is a rate for each session. So response time at time 0 for age 80 is the intercept, which is session 1. Let's see. How about the effective age then? What does that tell me?
Every year that you are older, you are approximately 30 milliseconds slower in responding.
Yes, for every year older you are 30 milliseconds slower. When?
In responding? No?
In responding, when?
At time 0.
There we go, at time 0, session 1. And that's because of these interaction terms. If these weren't here, then the sentence, for every year older you are, you're slower by 30 milliseconds is enough. Because that would imply parallel trajectories for people of different ages that just have different starting points. Yep. And I think that's significant, memory serves. Yep. The other 2 interactions are not, but I don't care. We're going to practice interpreting them anyway. So what is happening to the slopes that are both negative in older people? More negative the older you are. So exactly right. So an 80-year-old has a first slope of minus 164. If they are 81, we would add 7.6 to that. And it's more negative, which means are they improving faster or slower? Improving faster. Yeah, more negative is a good thing.
Better, you have more room to.
That's right. If you're slower to begin with, you've got more room to improve. And the same pattern with this one here. So slope 2.6 becomes more negative by 1.35 per year of age. If I go the other way, what happens to the effective age between sessions 1 and 2?
It's less meaningful. impact of age per year is only 22? No?
Yeah, everyone's like, this hurts. Yeah, so it's 29 at the first occasion, right?
Yeah.
So it is going to be less positive. The slope of age is less positive by 7.6 at session 2. So I would say age matters less in the second session. The differences as a function of age have been reduced. So the key to getting the interpretation of the interactions right is to always talk about what happens to a slope, not to talk about what happens to the predicted outcome. So the other way to talk about these interactions is what happens to the effective age. Because it is positive and these are negative, I would say the effective age is less positive or smaller. So it's reduced by 7.6 at session 2, and after that it is further reduced by 1.4 per session. So if we go down to the predicted outcomes, we will see that in just a second. Backing way out because I have to get this on here. I have looked and looked, folks, for a less painful way to do this, and I have not found one. I'm not going to say that that means there isn't one, simply that I have not found it. But the contest MD function, this is the analog to the test statement in Stata. It is also the analog to a contrast statement in SAS. What I am doing is saying, hey, can you take the slope that is in this spot in the output, and that one, and simultaneously test them all against 0. So we're not adding the 3 slopes together. The parentheses stop that from happening. What we're doing is a joint hypothesis test of if we took these all out, how much would the model suffer? And that will give us this F-test. 3 degrees of freedom, because we're testing 3 slopes. 99 denominator degrees of freedom. Hillary, you had asked me about this, I think, on Tuesday. All the other packages give you a 99 somewhere, including Stata, so then you can figure out what that would be for your margins. And F is significant at 0.009. However, if I go to the output, as a whole, these 3 slopes improve the model. But what do you think about the need for all 3 of them? Yeah, like the F on the whole is significant, and it's a per slope measure, but it looks like the main effective age here, the effective age on the intercept, is what's doing the work. So I would argue that if I were going from a parsimony perspective, I could probably remove these interactions, and the model prediction, would not be diminished. By the way, in your head, it might be helpful to do this to your output. Like when you see a main effective age, like that's what it's doing. It's modifying the intercept in the same way these are modifying the slopes. So age by intercept, age by time is what we have in the model here. So that's not what it says, but if I ran the world, that's how I would print the output. Question?
So could you run like the same joint hypothesis test with just the interaction terms
Sure.
and see if that, okay.
Yeah, that's a great idea. I did not do that, but certainly one could. The thing about testing each of these uniquely is that to some extent these are going to be correlated. And so their joint contribution may be larger than what it appears based on their individual contributions. You could do a joint F-test for just the 2 interactions, which will probably be non-significant, and then you can use that as justification for booting them from your model. So then, in terms of getting follow-up pieces of information, I have the model equation here for the fixed effect predicted outcome repeated for convenience. So I can get a simple slope 1, 2 and 2, 6 for any age by going into here and saying, all right, I need all the terms that have slope 1, 2 as part of them. So I need that one, and I need that interaction. Same thing for 2, 6. And then that forms the ingredients that go into these contest 1D statements. So 0 means I don't need the intercept, thanks. 1 means I do need one gamma 1O, don't need either of the next ones, and then in here I need to plug in the value of the moderator for the interaction. So I plug in the value of age for which I want slope 1, 2. And then I do the same thing for slope 2, 6 with the second interaction spot. So it is imperative that you go through your output and make sure it is in the order in which you think it should be. Because that is what the places of the zeros and the ones are referring to, is what ended up happening, not necessarily what you wrote. So these print out nice and ugly, like one line by line by line, and I don't like that. So I stole the table from SAS, which is better organized. Sorry, not sorry. It's one of the things I like about it. So if I look at slope 1, 2, you can see the differences, that the slope becomes stronger in older people. So I can make a picture out of that. And same thing with slope 2, 6, it becomes stronger in older people. The other way to talk about it is what happens to the effective age. And so here, the 1 in each spot refers to the main effective age, is what we need at a minimum. And then note the values that go into the interaction terms are the values that I coded the piecewise slopes with. So this should match exactly how you built the variables. And then we see the results as anticipated. The age slope is lower by about 7 between 1 and 2. And then after that, it gets lower by 1.3 or whatever the coefficient was here from before. All right, so we have significance tests up the wazoo. We got simple slopes up the wazoo. How about effect size? Should we care about that? Probably. We need to give people something. I'm sure there's lots of debates about what kind of effect sizes. I'm going to give you 2 that I think are complementary. One question is just, how much variance did this model account for? Like, how much of response time is because of practice effects and age? That's a more global kind of effect size question. So I have a little function here. I'm comparing the unconditional model that just had the 2 slopes to my new model, model 2 here, that is including age. And my function ran the correlations, computed the R-squares, and spit out the difference. So the total for the first model for the R-square was 0.037. Now it's up to 108, so a change of about 7%. So response time as a whole has increased the amount it's being predicted by 7% between the 2 models. Now, how well did each term do is a more specific kind of effect size. That's where pseudo R-square comes in. Now, the hard part, at times, is figuring out which should have been reduced by what. Because you got 4 variances here in this model to choose from. That means there's 4 potential R-squares. So the intercept R-square, so I have the base model. So the base model is the unconditional model. So this is like the empty model with respect to the level 2 variances, where all the variance in the intercept and the slopes is yet to be accounted for. That's these numbers right here. These are the variance components from the age model we just looked at. And so then the question is, by how much did each of these original variances get reduced after adding age? So it looks like for the intercept, we have an R-square of about 11%. Which term did that? Your choices are age, age by slope 1, 2, or age by slope 2, 6. Got 1 vote for age.
We're just looking
2
at the
votes?
intercept, so it has to be age.
It's the intercept. The rumors are all nodding. What do you think, Zoomers? Main effective age? Ding, ding, ding. Yep. It was the only one that was significant, so that'd be a good guess for no other reason. But yeah, of all the reasons why some people are better when they start this task, the first time they do it, age is 11% of that. That's what we know. So this is a more specific effect size that goes with each of the roles of age in the model. How about of the slope 1-2 variance, we got about 2% of that. Which one did that?
Age by slope 1, 2.
Age by slope 1-2. And it was not significant. Slope 2-6 is down by about 1% maybe. Question?
Yeah. When we're talking about significance, we're talking about like p-value from the test, right? Okay.
I am
There's not like a separate p-value associated with like the R themselves. Okay. Yeah.
Nope, I think you can talk about it as if there's a one-to-one mapping, because each of them has a distinct role to play. The math, though, does not work out that cleanly. So like what you'll see is these things go a little up, a little down, because they're all being estimated simultaneously. There is another way of computing these types of pseudo R-squares that uses, rather than two comparison models, it tries to anticipate what the overall variance would have been in the reduced model by putting the part that the fixed effects did back in there. That's the Wrights and Sturba version of it, and that's on your reading list for this unit as well. I'm not using that for a couple reasons. One is that it's harder to translate across packages, and this is more transparent. Number two is that they don't have a category for explained slope variance in the way they compute things. They put slope variance in the explained pile, like as an explainer. And I'll just agree to disagree on that score. So we're not doing it. But yes, those three p-values, I think you can say, like, this R square is significant because that is what the role of age as a main effect is doing. It's reducing this variance. And these ones are effect sizes for p-values that are non-significant. So it should theoretically match. And the residual has a minus sign in front of it, meaning there's eventually a number here, but the residual was not reduced at all. Coincidence or consequence? Consequence, because age is time invariant. So by itself, like there's nothing for it, it should not have changed E in this model. In this model. It can though. We're not there yet. So on the whole, how much more variance in response time did we get? 7% more. How well did each of the age fixed slopes do in predicting its corresponding variance? This much. All right, other questions? At some point, the pseudo R-square thing becomes impossible to talk about and keep track of. I had a paper with a 3-level model that had like 9 variance components in it, and I was just not going to do that to the readers. So I was like, it's 7%, the end. Write the authors if you want more numbers than that, but I'm not going to do that to you. So I think that both of these things are useful for different reasons. Okay, so in the world of cognitive aging, even though I know that my 2 interactions with age are non-significant, I'm going to leave them in. I am making that decision so that I can say I have fully controlled for age. If I take them out, that might be a reasonable thing to do. But then I can't say that I've fully controlled for age by only having it as a main effect. I've controlled for effects of age on the intercept. I have not controlled for effects of age on the slopes. So if you think about this from a regression perspective, and you look at the model, like each of these has some prediction to happen and some kind of residual afterwards, a leftover component. To control for age in just one of them is insufficient. So I want to say I controlled for age fully, leave me alone. I don't want to talk about it anymore, and I'm going to leave them in the model. Okay. Lots of code, lots of code. Reasoning. Should we look at a second predictor? Why not? So this would be more of a substantively meaningful predictor, a measure of abstract reasoning as a proxy for fluid intelligence. Are smarter old people better at this? We'll find out. So I have Rees with an I subscript, minus 22, because that was near the mean of the sample. And someone tell me why this is gamma O2 right here.
Is this the second thing that predicts the intercept?
It's the second thing that predicts beta 0. Likewise, this is gamma 1, 2, because this is the second thing that predicts beta 1. And this is the second thing that predicts beta 2. It's like a grid. So the full picture looks like this then, putting everything together and writing it out so that you can clearly see the interaction terms. Adding this to the Stata code looks like that. Got some Stata output first. Okay, so my constant, that's still my predicted response time at session 1 for an 80-year-old, and also, yeah, for someone with average reasonings, 22 in this particular sample. The reference growth curve is also specific to an 80-year-old with reasoning 22. We still have the same age effects in here. They have changed to some extent. Is that surprising? Probably not. Do you think age and reasoning are correlated? They are. For better or worse, they are. So the same principles that you learned in terms of what people would call multicollinearity in regression, when predictors are correlated, their effects are different when you put them in the same model when they're in different models. Same thing here. So and more specifically though, it's like these main effects here would compete against each other for intercept variance. These interactions with slope 1, 2 would compete against each other for that variance. So the collinearity aspect happens sort of per submodel in this type of framework. These age slopes, are they conditional on anything? Are they conditional on time? Are these ones conditional on time? We'll break it down into pieces. The age slope varies by time, right? This age slope is conditional on session 1. Are any of these conditional on reasoning?
They're all conditioning on like average reasoning. That's for average reasoning.
Well, that's my question. Are these age slopes specific to reasoning 22 or not?
I say yes.
Got one vote for yes.
Intercept usually works.
Well, I'll back you.
I don't know if that's wise, but thank you.
Well, we have 2 yeses that these age slopes are conditional on reasoning. So, we got a few nods and a few head shakes.
Oh no.
I guess my reasoning is that if the constant, if our intercept is conditional on age and reason, then it would also stand to reason potentially that age is conditional on the mean reasoning, and reasoning is conditional on the mean age.
Okay, so the logic being offered here is if the intercept is conditional on age and reasoning, then I think the age slope should be conditional on reasoning and the reasoning slope should be conditional on age. I would say that we're missing one piece of this, and it might be a language thing. So in the regression class, I'm introducing terminology of unique marginal versus unique conditional in describing these slopes, where the unique part, I think, is what you're talking about. It's like this is the effect of age after controlling for reasoning. This is the effect of reasoning after controlling for age. I agree with that. Likewise, like this is the effect of age on slope 1, 2 after controlling for the effect of reasoning on slope 1, 2, and so forth. But my question was more specific. Like, is this age slope not just controlling for reasoning, but conditional on reasoning 22 specifically? That's my question.
So like if we changed reasoning 22 a bunch of times,
Would that move?
age change at all?
Yeah, that's my question. Okay, so you're saying no now,
Because there's no interaction.
because there's no
of
interaction.
age and reason.
Yes, and an answer from the Zoomers, there is no, there is no age by reasoning anything in the model. So you're correct if you mean this is controlled for reasoning, but it is not specific to reasoning 22. If we recentered reasoning at some other point, this age slope would be exactly the same. Yep. So in this case, the effects of age and reasoning are additive. Like this is the effect of age, and we add to that the effect of reasoning, and then there's my prediction. The same thing happens with respect to these two interactions and these two interactions. So this is the effect of age after controlling for reasoning at session 1. These are the effect of age on the change slopes after controlling for the effects of reasoning, but they're not conditional on anything else. So if we go to reasoning then, what happens in smarter people? The slope is minus 27 for reasoning. Yeah, response time is lower, I would say by 27 per unit of reasoning, whatever that is. I think per additional question answered correctly or something like that. But is my sentence done? Nope. What's the end of the sentence?
When controlling for age.
When controlling for age and when.
And at time 0.
Yeah, this is at the beginning. So just picture like intercept hashtag reasoning 22 in your head. I think that will help. So yes, this is the effect of reasoning at the beginning because of these interaction terms. And as long as these are in here, we would expect a different effect of reasoning at subsequent occasions. In smarter people, what happens to slope 1, 2? As reasoning increases, what happens to slope 1, 2?
They improve more.
More negative slope, improve faster. Yep, improve more. What about, oh, saying I had the wrong one highlighted, but same pattern. What about slope 2, 6? Different pattern.
Smart people actually don't improve as much.
Yeah, minus 35 is the slope, and the interaction term is a positive 3, which means as reasoning increases by 1 unit, slope 2, 6 slows down, or is slower, less negative, by 3. However, I don't think these things are, oh, that one is. That one's significant, the first one's not.
Is it back to, again, like they had less room to improve to start with, maybe?
So the first one, like they have less room to improve, which would, like that one wouldn't make sense, but if you look at the standard error, like this, it's basically 0. This one, yeah, it looks like there is, they have less room to improve subsequently, a little bit. That's not going to be a huge effect, I can tell you that, but it is significant. So take that as you may. So yeah, the same patterns happen. If I go with the effect of reasoning, differences between people as a function of fluid intelligence. Minus 27 at the first occasion. What happens to it at the second occasion? Does reasoning matter more or less? More. Yeah, more negative. But then after that, after 2, does it matter more or less? Minus 27 and a positive 3. Less, yeah, they're working against each other. Yep. So we can ask for that, but here's a picture. Because you need to do your readers a favor and give them a picture. Zooming all the way back out here. Where'd my picture go? There it is. And yes, I made this in Excel. Sorry, not sorry. I know there's ways to do it in all the packages, but at some point I just gotta quit and get the handout done. Plus, For those of you who work with other people who are not good with R, make their pictures in Excel so you can give it to them and they can tweak it however they want. Because then they can change the axes and the titles and the font and the lines, and they can fuss with it all you want, and they don't have to be like, can you rerun this and do this? Can you rerun this and do this? Can you rerun this and do this? Hypothetically, of course, that has never happened to me, but Excel is your friend in collaborating with folks. So what I have here then is the expected change across sessions, and it looks bent like this because this is a piecewise model, so that's on purpose. And I have plotted plus or minus 1 standard deviation roughly around the mean. So reasoning 17 is the circles, reasoning 22 is our reference growth curve, the squares, and reasoning 27 are the triangles. And note, I'm still calling this a growth curve, even though it's not growing and it's not curving. If that makes you feel weird, you can say a change function or something like that. Trajectory, that's a word people like to use. So people who are smarter, the triangles, are faster to begin with. They're a little bit faster in change, it looks like. That's non-significant. But then the slope is shallower after that. So the people who are slower to begin with have stronger slopes going from 2 to 6. Yeah, and so here's the corresponding variance components for that. We can see how much those went down in just a minute. So the first 3 rows are the ones that we're going to be saving. Random effects are still negatively correlated, so people who start out higher change more, because change more would be the lower value on the individual slopes. Reasoning does contribute overall to the prediction on the whole, but it looks like only 2 of the effects are actually significant if I go into the table. The main effect is, and the effect on the second slope. Then we can get simple slopes for any level of reasoning. So I've got the slope 1, 2 for each of those levels, and the slope 2, 6 for each of those levels. So I can then put, if I wanted to, p-values on these lines, just to say which ones of these are significant and which ones aren't. I could do regions of significance as well. Change in R square, so R square for the overall model is up to 0.16. So I'm getting that by saving the results of this model from terms of the predicted outcome, correlating it with the real one, saving that correlation, squaring it, and then feeding it into here. So we've increased our R square relative to the previous model by 0.05. So another 5% of the overall variance in response time is attributable to abstract reasoning. Figuring out where my stuff is in here, 3 more terms being added, and then here's the pseudo R squares. So I don't have a pretty table, but this is what it looks like in this data output. So 15% of the intercept is what we have now relative to the empty version of this model. So relative to the first version with no level 2 predictors, age and reasoning together have accounted for about 15% of the intercept variance. Then the question is, how much more did reasoning get that age didn't? And I'm actually computing this differently than I did in the book. I've decided I don't like how I did it in the book, and I'm going to fix it. Because what I had done before was, like, each new model was like the new total. And it's like, okay, so I got 3% of this. Now, of the percent that's left, how much percent of that did I get? And it's like this daisy chain of the, and I don't like that. So I am computing this relative to the unconditional model as the one that has the most possible variance, like the total. So I know that age and reasoning accounted for 15% of the variance. I can then compare that to what I got before and say that that's an additional 4%. So we were at somewhere between 10 and 11 before. Now we're up to about 15, so the change is right here. So an additional 4.2% of the variance in the intercept is attributable to abstract reasoning. So pseudo R square for each of the slopes computed the same way, and the changes. So this one right here is interesting. The change in the pseudo R square for slope 1, 2 is negative. What's that mean? Yeah, you got more variance than you had before. That theoretically shouldn't happen. It happens all the damn time. I'm surprised when it doesn't happen, quite frankly. These things shift around. Like they don't obey numeric like rules of things. And even in standard linear regression, you can have negative R-squares if you're looking at adjusted R-square. The difference is that in sums of squares land, they're computing R-square using total sums of squares and model sums of squares such that R-square can never be 0. But if you compute adjusted R-square, that works out to be the difference in mean square error. Instead, that can go negative. So for the same reasons, this can go negative, and I would report it as 0 in that case. It accounted for no more variance, and may have even hurt. So yes, pseudo R-square is called that for a reason. These numbers are wiggly. We did improve the pseudo R-square for slope 2/6 though by 7%. And that is a function of that interaction term of reasoning by slope 2/6 being significant. Then the change in the R-square for the residual is again 0, as expected. There we go. All right, R folks, new terms added for you are right here. So now note that I had to do this in a weird order. In Stata, I put it in so that the new things in the model are at the end of my code. I'm used to doing it that way. So I added reasoning as a main effect, and then the 2 interaction terms at the end of my code. And Stata's like, okay, here you go. This is the order you wrote it. This is the order I'm going to print it for you. Elmer is like, no, actually, I know better. You didn't mean that. Let me do what I think you meant. So I had to stick reasoning right here as a main effect, and then put the interaction terms. And I didn't have to do it that way, but the reason I did do it that way is because it will rearrange it into this.
So main effects always first.
Main effects are always first. Yep. And that matters when you're going through this nightmare of 0s and 1s and values, because they have to be in the right order. Just when you thought I was almost making friends with R. Not quite. So in your homework, when you're doing these kinds of things, if these values don't work, check the placement. That would be my #1 suggestion. Make sure it's matching, and that you don't forget the fixed intercept being first, which is why I always put the 1 in here to remind myself when I'm going down my list as to what spots go with which of these things. So in this set of codes right here, I am asking for simple slope 1/2s, so that's why the 1 is turned on where that main effect is. And then reasoning by that is turned on in the spot of the interaction term with the values of the moderator of reasoning. Same thing for slope 2/6 in the next spot, and then the interaction terms with reasoning in the last spot. The simple, simple age slope at each session, that should be reasoning. My bad. That has the reasoning slope turned on all the way through, and then these are the values of slope 1/2 and 2/6 that go with that for the 2 interaction terms. And here is a nicer table of pseudo R-squares from the first model with age only, the second model with age and reasoning, and then here's the differences. So you can see the -1 there. It just happens. Now, in terms of revising this model, I have a choice to make. I already decided I'm going to keep age in, these interaction terms in, because I want to say I fully controlled for age. Reasoning may not have the same status as a predictor. Like some predictors are like, I tried it, didn't work, I took it out. This might be one of those. For the sake of interpretation, though, I would make a decision to leave in this non-significant interaction, because otherwise the interpretation of slope 2/6 is not the same. So slope 2-6 is coded 0, 0, 1, 2, 3, 4. Without this interaction term in the model for reasoning, the interaction of slope 2-6 and reasoning would not be the change after 2. It would be 1 and 2 lumped together because they're both coded 0. So for the sake of just clarity of interpretation and making sure that slope 2-6 means the same thing every time I'm looking at it, every spot in the output, I'm leaving this in. All right. Picture time. How are we doing? It's not difficult, it's complex.
I think it's difficult.
Like, it's each of these pieces is something you're familiar with. It's holding on to all of them and keeping them organized is the hard part. I feel like that's complexity and not difficulty, but that may be a subjective interpretation. The complexity is real. All right, so then, what you can be working on over break, or not until Monday morning, take your pick, of next week is a formative assessments. We have one of those to do on the Tuesday we get back. We will have another one to do, and I'm saving that one for the very last day of class. So you'll have the last one will be due Wednesday of the last week of classes instead. So we can talk about, it's going to be a story problem. So we can talk about that and a few other stories. I will let you know once your last homework is available, probably not until after break though. So you can have real breaks. Yay! Yes, we all need a break, don't we? Amen to that. All right, then how about I give you 5 minutes of your life back? Fair? I'm so generous, I know. All right, thanks for being here. Have good breaks, take care of yourselves, and I hope to see you on the other side.
You too.
Bye for now.